A wonderful day to everyone. We are continuing our studies in Math 23, and our lesson for today is on double integrals over rectangles. Let me first introduce myself. My name is Marik Neri. This was my photo a few years ago. And I have a PhD in mathematics, and I am also currently an associate professor at the Institute of Mathematics in UP Diliman. Now, if things go back to the way they used to be, and you happen to visit Math Building, my office is in room 217. Otherwise, if you have concerns regarding our lessons or you have questions related to our studies, you can send me an email at this address. Now, for the sake of conserving our bandwidth, I will be uh, stopping my video for a while. Okay, so let us go to the main content of this lecture. Our study will be on double integrals over rectangles. Now, if you recall, our problem way back in Math 21 was what is the area of a region bounded by the curve y equals f of x, the line x equals a, x equals b, and the x-axis. Now, this is how we went about in setting that up. So first, we let f be defined in the interval AB, and then we subdivided the interval AB into n subintervals of length delta x. So to illustrate, we have this figure. Now, the subintervals technically need not be of the same lengths. Okay, so you can have different lengths, but for the sake of ease and convention, we can set the subintervals to have equal lengths delta x. And then in each subinterval, we choose a particular point. For example, in the ith subinterval, let's choose the point x sub I star. Then we defined the definite integral of f from a to b, given by this notation on the left. And this definite integral is simply the limit as n approaches infinity of the Riemann sum f of x I star times delta x. I runs from 1 to capital N. Now, if this limit exists, then that's the value of the definite integral on the left. If, moreover, our f of x is greater than or equal to 0 in the specified interval AB, then the definite integral gives us the area of the region bounded by x equals a, x equals b, the curve y equals f of x, and the x-axis. Now, we will be extending this problem of the area into solids. And for solids, we are concerned with the volume. Now, let's start with a very simple solid, the rectangular solid, or sometimes it is called the rectangular prism, with length L, width W, and height H. Now, what is the volume of this solid? Very easily, if you recall, the volume is given by the product of L, W, and H. Now, this rectangular prism will be our basic material in finding the volumes of solids in general. Now, consider a rectangular region on the xy plane. So the rectangular region R is denoted by the cross product of the intervals AB and CD, where AB is the interval for x and CD is the interval for y. Also, suppose that our function f is continuous on R and it is non-negative for all points in R. So to illustrate that, so here on the x-axis, we have the interval AB, and on the y-axis, we have the interval CD. So we form the rectangular region R on the xy plane. And then the surface for f of xy is this bluish region here. The solid that we form would be topped by the surface of f and then by the vertical parts of the planes and the region R at the base. So what is the volume of this solid? So you can look at the solid here as a piece of bread, and you're interested, what is the volume of this piece of bread? So to do that, what we first do is we partition the region R into subrectangles. So we divide AB and CD into subintervals. So dividing our interval AB into subintervals, we form M columns. And then dividing our interval CD into subintervals, we form these N rows. So we get a total of M times N subrectangles. And the length of the subrectangle is delta x, and its width is delta y. Now let R sub ij be the ijth subrectangle. And the area of this subrectangle is simply the product of the length and the width. So it's simply delta x times delta y. Now what we do now is we want to get a rectangular prism. So instead of using the subscript ij, let's just use a subscript k. So let's denote the ijth rectangle to be the kth subrectangle. So what we do is we just take any arbitrary point in this kth subrectangle. Okay, so that point will be x sub k star, y sub k star. And then we take its particular point on the surface. So the point on the surface corresponding to the point that we selected will have a z coordinate f of xk, yk. Okay, so then with this height, we can form the prism with bases rk and height f of xk, yk. What is now the volume of this prism? Again, it's just the area of the base times the height, which is up to the surface f. So the volume is given by f of xk, yk times the area of the base. So the volume of the entire solid is approximately the sum of the volumes of the rectangular prisms. Okay, and it is given by this Riemann sum. And so if we increase the number of subrectangles by increasing the number of subintervals, in that case, technically what happens is the delta x goes to 0 and the delta y goes to 0, or in other words, the value n, which is equal to m times n, the total number of subrectangles goes to infinity. Our approximation becomes more accurate. Okay, so these are illustration. So the smaller the subrectangles we use, the more accurate the approximation becomes. And as n approaches infinity, we get the exact volume of the solid. And this volume is given by the limit as n approaches infinity of the Riemann sum. Okay, so this limit is defined to be the double integral. So formally, the double integral of f of xy over the rectangle R is defined as the limit of the Riemann sum. And we denote this by the symbol. We have this double integral symbol on the left side over the region R of f of xy dA, provided that this limit exists for every choice of xk, yk, and rk. Now, the dA, we can replace the dA here by dx dy, okay, or dy dx. So recall that the delta A is equal to delta x delta y. So when we get the limit, notation-wise, our dA is equivalent to dx dy. Now, if this limit exists, then we say f is integrable over R. Now, some remarks. In general, the double integral gives us the net signed volume of the solid bounded by the surface, because we can have a part of the curve or of the surface which is above the xy plane, and also a part of the surface which is below the xy plane. So the double integral, you just get the net. So it's the volume of the portion above the xy plane less the volume of the portion below the xy plane. Now take note that the Riemann sum may take several values depending on the choice of partitions with subrectangles R sub k and the choice of the arbitrary point xk, yk in Rk. So for instance, you can take a sequence of subrectangles. You go horizontally, then you go up horizontally again, then you go up horizontally. Or you can go vertically, then you go down vertically, then you go up vertically as you move from one column to the other. So you may have different values for your S sub n. The important thing is the totality of it. Okay, the totality will give you the same value. Now we have this very important theorem. If our function is continuous on a rectangle R, then we say f of xy is integrable over R, meaning the limit of the Riemann sum will always exist. Okay, so again, if f is continuous on R, then f is integrable over R. Okay, so this is different from our differentiation. If f is differentiable, then it is continuous. Okay, if it is continuous, it is not necessarily differentiable. But here, if it is continuous, then it is integrable. And there's also the double integral satisfying linearity conditions. So first is the double integral of a sum is just the sum of the double integrals. And secondly, the double integral of a scalar times a function is just the scalar times the double integral for any real constant k. Now, how do we evaluate a double integral? We don't want to perform the partitioning, the approximation, and then the evaluation of the limit. That would be very terrible. So we need some approach to evaluate the double integral. For this, we need what is called the iterated double integrals. How do we do this? Suppose that we have an integrable function f on the rectangular region R. Take note that if we have this definite integral here, the integral from c to d of f of xy dy, take note that when we integrate this, we integrate with respect to y. So that means we are holding x fixed. Okay? So this is called a partial integral of f with respect to y. Now take note that when you integrate this with respect to y, and then later the y will take the values c and d, then the resulting function will be a function of x because you fixed x, so x is still there. So the result is a function of x, so I of x. Therefore, if we get the integral from a to b of I of x, then that is the same now as the integral from a to b of the integral from c to d of f of xy dy. Then we have dx outside. Okay, so because this integral inside is just I of x. Now, for mathematicians, we can remove the parentheses. We don't need to be too formal about notations. So we just simply write this as the double iterated integrals from a to b, and then from c to d of f of xy dy dx. Take note that the order of integration is you start from the inside integral going to the outside integral. That's how we evaluate it. We start from inside, then we go outside. Okay, and this is called an iterated integral, specifically an iterated double integral. Similarly, if I have this expression here, so we will be integrating with respect to x, fixing y. So this is called a partial integral of f with respect to x. And then the result will be a function of y. So if we get the integral from c to d of I, then that is the same as the integral from c to d of the integral from a to b of f of x, y dx. And then we can drop the parentheses and we have this expression on the right. So you integrate first with respect to x, then the result you integrate with respect to y. Okay? So how do we relate these iterated double integrals with the volume? Okay, we will look at that later on, but for now, let us have some examples. So evaluate the following iterated integrals. So for the first one, so we integrate the inside integral first. Okay, so we fix x, we evaluate the integral with respect to y. So using the power rule, we just have 6x squared y squared over 2, and that makes that 3x squared y squared minus y. Evaluated from y equals 0 to y equals 1. Now the evaluation of what's inside is 3x squared minus 1. And then we evaluate with respect to x. So we get x cubed minus x evaluated from 1 to 2, and that gives us 6. Okay, so the value of this iterated integral is 6. How about letter B? So take note that this looks similar to our problem in letter A, except that we now evaluate with respect to x first, and then we evaluate with respect to y. So the question is, are we getting the same answer, 6? Okay, you may want to pause the video for a while and try this on your own. Okay, so let us continue. So integrating the inside, we get 6x cubed over 3 times y minus x. And that simplifies to 2x cubed y minus x. And then when x is 1, when x is 2, minus when x is 1, we get the simplified form here, 14y minus 1. And then we evaluate from 0 to 1, we get 7y squared minus y. From 0 to 1, that will be 7 minus 1, and that is 6. Okay, so this is very nice. So it appears that the iterated integral, you can switch the integrals and then switch the position of dy dx. But can we always do that? So that is the result of the study of Mr. Fubini, and he gave us this theorem. Suppose our f is continuous throughout the rectangular region R, then we can write the double integral over R as either of the two iterated integrals. So the first line here gives us a way on evaluating the volume of the solid. So we just evaluate the iterated double integral over R. Okay, so take note here that the interval for x is from a to b, and the interval for y is from c to d. And this iterated integral, if it exists, gives us the value of the volume of the solid. Now, since we are dealing with a rectangular area, this is also equal to commuting the integrals and also the dx and the dy. Take note that this can only happen if you are dealing with a continuous function f over a rectangular region. If the region is not rectangular, then Fubini's theorem will not automatically apply. Okay? So let us evaluate the area of the volume of the solid bounded by y sine xy above, and the rectangular region 0, 2 in the x and 0, pi in the y. So take note that if we integrate with respect to to y, it will be difficult because you have a y outside and then you have a y sine xy multiplied to it. However, if we integrate with respect to x first, that's very easy. And so we can set up the integral to be, the inner integral will be with respect to x. Okay, so the bound is from 0 to 2 for the x, and then outside is 0 to pi for the y. And when you evaluate the inner integral, you just fix the y. And so we have, we let u be xy, so du will be y dx, and that accounts for the y dx there. And so you will get a sine u. The antiderivative for sine u is negative cosine u, and that is negative cosine xy, evaluated from x equals 0 to x equals 2. And after evaluating, we have this result here. And then integrating now with respect to y, we get negative sine of 2y over 2 plus y, evaluated from 0 to pi. And the answer there is pi. So the volume would be pi cubic units. Another example. What is the volume of the solid under the surface f of xy equals 4 minus y squared above the region? So x is from 0 to 3 and y is from 0 to 2. Okay, so take note that this is our figure here. So our x is from 0 to 3. So this is the x-axis there. And corresponding to the y-axis is 0 to 2. Okay, so this figure was made in MATLAB. So that's why we have this orientation for the axis. And then our cylinder is given by this 4 minus y squared. Okay, so the rectangular region is given by R. And the volume can be solved using the iterated double integral. Okay, so our x ranges from 0 to 3, and then our y from 0 to 2. And then we can easily evaluate with respect to x. We get a 4x minus xy squared. And then when you simplify, you get 12 minus 3y squared. And then we evaluate the integral with respect to y, evaluated when y is 2 minus when y is 0. And what we get is 16. So the volume would be 16 cubic units. Okay. Now, to end this part of the lecture, we have a neat example using Fubini's theorem. Okay, so evaluate this double integral e to the x cosine y dA on this rectangular region. Okay, so take note that we can just give any ordering. We can have dy dx, or you can have dx dy. It really doesn't matter. So, but for now, let's say we have dy dx. Okay, so if this is dy, then the inner integral will be on the interval for y. And then dx is outside, so the outer integral will be the interval for x. Now take note that when you evaluate with respect to y, e to the x is independent of y. So it is a constant with respect to y. So what we can do is we can put the e to the x outside the integral. So if you remember, that's a property of definite integrals. The integral of a scalar times a function equals the scalar times the integral of the function. So we can place the e to the x outside the first integral, or the inner integral. And take note that when you evaluate this will just be a constant because the definite integral is a real value. So this is a definite integral, this is a constant value. And since that is a constant, we can put it outside the integral. Okay? And so what happens is, rewriting it in the form of the integral, voila. So it appears that to evaluate this integral, you can separately evaluate the two partial integrals, and then you just get the product. Very nice, okay? And so the first integral on the left gives you this, the second integral on the right gives you this, and the result will be the value here. Okay, so take note that you can only do this if the functions for x and the function for y are independent. So meaning the function for x doesn't involve y values, the function for y doesn't involve x values, and the region is a rectangle. Okay, so we will end with a set of exercises for you to do. So I will answer these exercises at the end of the second lecture. So I will leave this to you to try out for yourself. Okay?